Well, thanks so much, Anne. So my wife, you, me, we are the 5%, okay? We're just 5% of the universe. Everyone who you ever loved, everything you've ever seen, heard, tasted, touched in your life, everything that is on the damn periodic table that you've seen in school, everything you've ever heard, or everything you've ever been able to probe in a laboratory, all this stuff is just 5% of the universe. We know, astronomy tells us, that 95% of the universe is made of something that we have never, ever experienced. And to me, this is the most mind-blowing thing I've ever heard in my life. It's incredible and revolutionary to think that not only, the Earth is not the center of the solar system, not only there are planets around every star in the galaxy, and there are billions of galaxies in the universe, but all this stuff is just 5% of the universe. So this talk will be about the remaining 95%. And, this may sound crazy to you, but at some point in my life, I was really thinking, okay, why am I alive? Okay, so, obviously I love my wife. This is very important to me. But what am I doing? Why do I do this job in particular? What do I want to know? What would make me happy at the end of my life? And I thought, well, I want to know what dark matter is. I don't need to be the one who discovers it, but I want to know, by the end of my life, I want to know what this damn dark matter is, because I can't finish my life without finding out. So hopefully this will happen. We're not there yet, so at the moment we don't know. And so this will be my version of what this stuff is. Dark matter and dark energy are two different things, and they're both very important, and we need to try to understand what they are. And to understand what they are, we use big telescopes like Keck, because the only evidence we have of this stuff comes from astronomical observations. So I will guide you through some astronomical observations that eventually, I hope, will help understand what this stuff is. This is really the title of my talk, What's the Universe Made Of? And sometimes when I'm on a plane, somebody asks me, what do I do for a living? And if I'm in a good mood, I say, I try to find out what the universe is made of. And usually, that's the beginning of an interesting conversation. But so let's take the point of view of the Earth. So if we are on Earth, we think the right answer is the standard model of particle physics. You might have heard about this. It's basically electrons and protons and nuclei. But the view from the universe is completely different, right? The universe is made of dark matter and dark energy. And we learn about it using a tool called strong gravitational lensing, and I will describe that tool to you. And finally, I will tell you a little bit about how we plan on using adaptive optics to learn about this. So this is the view from the Earth, the standard model of particle physics. Everything, including my wife, is made of quarks, leptons, and then there are these force carriers, light, gravity, and a force called the weak interaction. So this is what particle physicists would have you believe. But we are astronomers. And when we look up in the sky, we see this. So this is the Hubble Deep Field that Anne was referring to. This is an image taken by the Hubble Space Telescope. And you see there are, just in this little portion of the sky that is probably as small as the eye of President Roosevelt in a dime held at arm's length, there are maybe 10,000 galaxies in this picture. We see this, but when we try to interpret this, we discover that really the universe looks like this. So if we had eyes capable of seeing dark matter, we would see that the universe looks like this. There are filaments of dark matter, and when these filaments cross, that's where you form galaxies. And within these galaxies, like the Milky Way, you form stars and planets and us. But really, the backbone is this dark matter. And so if we were to draw a cosmic pie, where the size of each slice represents the relative importance, The picture we have now is that only 4 or 5% of the universe is atoms, the normal stuff we're used to every day. 3/4 is what we call dark energy, and about 20% is what we call dark matter. Now, I know it's confusing. They're both called dark, and the names are horrible. The reason why they're called dark is that they don't interact with light. So they shouldn't really be called dark. They should be called transparent because they don't interact with light. And even though they're both transparent, they are different things. So I will try to explain briefly how they differ and how we learn about them. The question I'm trying to answer is, what are these things? I think we're pretty convinced, everyone that works on these fields is convinced that these things exist, and we know how much of each there is in the universe. What we don't know is what these things are, okay? So we know how much there is, but we don't know what they are. And so I told you that they are transparent, so they don't interact with light. So you see me because light from the lamp scatters on my face and bounces off to you. You see the stars because light emitted from the stars gets to your eyes. So the dark universe doesn't interact with the light, so we cannot see. Okay? It doesn't cast any shadow. It doesn't emit any light. The only way we've been able to see it so far is through its gravitational effect. So, like the Earth attracts me, and I'm standing here because the Earth is attracting me, in the same way, a lump of dark matter would attract me. Okay? So the only thing we see is the gravity coming from this stuff. So we need to learn about them using gravity because that's the only property we know they have for sure. And so the tool that I will be using is called gravitational lensing. So you're all familiar with lensing, optical lensing. So for example, my glasses are lenses. Okay? The Keck telescope are lenses. Gravitational lensing is a kind of lens where the deflection of light doesn't come from glass, but comes from gravity itself. So let me explain how it works. So this is an example of an optical lens. Okay, you're all familiar probably with something like this. This is a fish tank, you can see here. And there's a fish here. And now I'll play this movie. So pay attention to this part. As I play this movie, you will see, okay, the fish starts swimming, and see what's happening? There's another image of this fish. Okay, and then there's another image of this fish. So whenever, I'll play this again. So whenever these fish cross approximately this line, another image appears on the other side. Now this is a case of strong lensing by an optical device. It's the particular shape of the edge of the fish tank that is creating the two images of the fish. In the real universe, this happens because of gravity. Instead of having the edge of a fish tank, you can have a galaxy deflecting the trajectories of light so as to produce multiple images of a background image. And notice another thing. So the second image of the fish, okay, appears on the other side after some delay. The delay is very short, but there's a delay because the light has to go around and has to go through the glass. And as it goes through the glass, it takes more time because the light slows down through the glass. The same thing happens in the universe. As the light goes around the galaxy or around something like a black hole, one of the two trajectories will be longer than the other, and in some sense, the light will slow down on one side. And so the two images will not get to you at the same time, will get to you with a delay. So this is the basic mechanism we use to learn about the universe. So let me explain how we do this to learn about dark energy. So first, this is the same idea that I explained before. So what is dark energy? All right. Dark energy is nothing but a fancy name to say that the universe is accelerating. You probably heard this before in public lectures, but the idea is that if I throw this bottle of water up in the air, you probably know what happens. So if I throw it slow, it will come back to me. If I throw it very hard at the escape velocity from Earth, this will keep going at infinity, but slowing down. The funny thing that happens in the universe is that as the universe expands, instead of slowing down through the effect of gravity, it seems to be accelerating. This is equivalent to say that if I throw this bottle up in the air, instead of coming back or slowing down, this will be going up faster and faster and faster. This crazy phenomenon was discovered about 20 years ago and is what we call dark energy. The fact that the universe is not just expanding, not just everything is getting further away from each other, but it's happening faster and faster and faster. This phenomenon is what we call dark energy. We know about dark energy, for example, by looking at distant exploding stars called supernovae, and people have done this, and this is how the phenomenon was discovered 20 years ago, and scientists were awarded the Physics Nobel Prize in 2011 for this discovery. And there's many other experiments that tell us that this is happening. So I think pretty much everyone is convinced that this is happening. The universe is accelerating. But we don't know what exactly this is. Okay, so there's many possibilities. Einstein, many years ago, 100 years ago almost now, proposed something called the cosmological constant, which is a kind of modification of the laws of gravity. Another possibility is that it's called vacuum energy. Vacuum in between galaxies does not have zero energy, has some amount of energy. There are many modified theories of gravity that could explain this. Some of them are called string theory. There are many exotic explanations for this, but none of them seems to be convincing enough to be the leading candidate. So we have some ideas, but none of these ideas seem to be completely convincing so far. Whenever we don't have good theories, I, as an observer, think that it's better to get good data. And how do we get data? So remember the fish. So the fish, here I'm looking at the fish tank from another point of view. This is me. This is the source, so this is the fish. This is the edge of the fish tank, and these are the two images. And you see from this diagram that the image that is going this way has to go a shorter length than the image that goes this way. So if somehow I'm able to measure with the clock the arrival time of the two images, I can tell you what is the distance covered by the light. So I can use the difference in arrival time, the delay between the images, as a measurement of the size of the universe, of the scale of the universe. I do this many times. I can tell you how fast the universe is moving and how the universe is accelerating. This is what I use to learn about dark energy. Of course, you know about my favorite philosopher, Yogi Berra. He says, in theory, there is no difference between theory and practice. In practice, there is. This is one of my favorite quotes I always tell students in class. Theory is great, but, physics is an experimental science. We have to test it, okay? We have to see whether it works. And so how do we test this idea? Well, something really, really interesting happened a couple of years ago, and it does seem to be that this kind of phenomenon only happens when I fly to Japan. So I will try to fly to Japan more frequently, but let me tell you this story that was very interesting. So back in 2014, in November, as I was about to catch a plane to Japan, one of my collaborators, Pat Kelly, looked at this picture taken by our team using Hubble Space Telescope data. This is a galaxy in a cluster, lensing, like the fish in the fish tank, this background galaxy here into these multiple images here. And what he saw was these 4 images appeared between February and November 2014. And this is the difference. See these 4 spots. So we immediately understood these 4 spots were 4 images of the same exploding star. So a star had exploded in the purple galaxy here in the background, and the effect of the foreground galaxy was to produce 4 images of the background star kind of like what we saw in the fish tank. But this is not where it ends. This was remarkable. This was the first time this phenomenon was ever observed. But something even weirder happened. We realized that this was not the only image that we could expect of the supernova. And in fact, we realized pretty quickly that another image should appear here. An image was probably appeared here in the late 90s, 10 or 15 years ago, but we predicted an image would appear here. So we worked very, very hard to try to predict when the next image would appear. And we spent many months, and then we said, well, this is our prediction. This is our paper submitted October 19, 2015, again, from Japan. I don't know what's with Japan and supernovae, but that's how it works. And so this is where we predicted the next image to appear, sometimes between the end of 2015 and the beginning of 2016. This is the peak of the supernova. It was a time where Hubble could not point at this field because it was too close to the sun. So at that time, we had no clue of whether the supernova was there. And the soonest the Hubble could point at this field was October 30th, 2015. So October 30th, 2015, nothing there. So, okay, this is fine. Then we took another image 2 weeks later. Nothing there. We started to worry, maybe physics is broken, maybe, what we thought was going to happen didn't happen. And then finally, it was déjà vu all over again. Just to quote Yogi Berra again, who seems to be very appropriate for this kind of science. So in December, finally, this is December 2015, the supernova appeared exactly where we predicted and when we predicted it would appear. So this idea that you have multiple images appearing at different times is not just theory, it's something you observe in real life, okay? So we know this works, and we can do this. We can do this many times. And when we do this, this is a movie that is showing you what happened. So first the supernova, an image of the supernova appeared here in this image of the galaxy. This is like one image of the fish. Then on the other side of the fish tank, 4 images appeared more or less at the same time. And then finally, in 2015, an image appeared here. Okay, so this is equivalent exactly to the fish tank. As the fish moves, multiple images appear. So we can use this to learn about the universe. But the other ingredient we need, we don't need just the time delays. We also need to know exactly how the fish tank is made, okay? Because the arrival time depends not just on the properties of the fish, but also on the edge of the fish tank. So in order to reconstruct the properties of the edge of the fish tank, we need to take very, very high, very, very sharp images of the object that is acting as a lens. And these are images taken from the Hubble from Keck with the adaptive optics system, of one such system where there is a galaxy producing 4 images of a background quasar. And this is the lens light, the arc light, and the background quasar light in 4 images. So the entire image here is about 3 arc seconds. And the resolution of this image is better than what you can get from the Hubble Space Telescope. This was done at Keck using the adaptive optics system. So we combine all this stuff together. And this is where we're at the moment. So this is a bit complicated. Forgive me for a second. I will go into one slightly technical slide. So this diagram here is showing you 2 of the main parameters we use to describe this thing. And the important thing for you is to think about this red line. So this is Einstein's cosmological constant. So Einstein's theory for what this dark energy would be this red line here. And this gray area here is what the data like. As you see, there's a little corner of the data that is consistent with the red light, but most of the gray area is below the red line. Okay, so most of the area is not Einstein's dark energy. Now, this is not enough evidence to say that dark energy is not Einstein's idea of dark energy, but we're getting there, okay? We're getting to the point where we may be able to say that dark energy is not the kind of dark energy that Einstein predicted. It's a different kind of dark energy. And that's progress in this field, because when you don't, we're literally in the dark, right? So everything we can rule out is good. It's good news for us. The present and future of dark energy, I think there are hints that the simplest possible model might not work, which is very, very exciting, because there are two possible explanations. One could be that the measurements are imprecise or wrong, or the thing that we are all secretly hoping for is that this is really, I think this might be the beginning of a new cosmological model, okay? So, because I'll tell you a secret. There's nothing that physicists and astronomers love more to find out that they're wrong. Okay, so if we find out that we are wrong, well, if we find out that Einstein is wrong, that's the best, because, But if we find out that we are wrong, collectively as a community, it means that we are learning something. So learning something in science meaning learning that something is wrong. So we can never show that what we know is right. We can only know that what we thought we knew was wrong. So for us, finding out that something is wrong is the best that could possibly happen to us. It's a strange world, but that's how we roll, okay? We like to be proven wrong. So this could be potentially very interesting, but we don't know yet. We have to wait. So let's talk about the other thing, dark matter, my deepest passion. Okay, so what is this thing? Well, first of all, how do we know about dark matter? So the story goes back a long way, but I think one of the most important characters in this story is Vera Rubin, this person here. And she and other colleagues in the 70s were able to measure how fast galaxies like the Milky Way rotate, and they found out that these galaxies rotate way too fast. They rotate so fast that the only way to explain how fast they're rotating is by assuming that most of their mass is not made of visible matter. Okay? There has to be more gravity, more mass. It's kind of like, if I'm spinning something, with the rope, and I'm spinning it like this, the rope has to have some tension in order to keep that from leaving my hand. And so the tension in the rope is dark matter, okay? So really galaxies are kept together by dark matter. And now we've seen this over and over again. At all scales, the mass of the universe is dominated by something that is not us, it's dark matter, okay? So this is the evidence we have. But we don't know what it is, okay? So we know it's not the standard matter, we know it's not atoms. There's many possibilities. If you talk to particle physicists, they would like to say that it's a light supersymmetric particle. But they have hundreds of ideas. They have such a variety of ideas, and maybe one of them is correct, or maybe none of them are correct. And they have all these fascinating names that probably mean nothing to you. I think they mean nothing to most of us. But the interesting thing is that we can probe these properties, because the properties of these particles affect how they will make up the building blocks of the universe, okay? Let me illustrate this with a simple example. So this is a simulation done in a computer of a galaxy, and this is the same galaxy simulated in a warm and cold dark matter. These are two different flavors of dark matter, and you see the difference here. The one on the left is very lumpy, has this fine structure. There's lots of little blobs. This one is much smoother. And so one way of distinguishing the flavors of dark matter is to measure how smooth or how lumpy mass is on the scale of the universe. Now, to go back to my fish tank analogy, what I'm looking at what I'm interested really in is how smooth is the glass, okay? Is the image of the fish sharp, or is the image of the fish all blurry? Because you see, these little balls of dark matter here will really behave like little dents in that fish tank, okay? So by looking at very carefully at the dents in the fish tank, I can tell you whether the universe is of this flavor or of this flavor, okay? But I need to have a lot of precision in order to tell the dents in the fish tank. And let me illustrate this with an example. This is a group of galaxies. There are 3 galaxies here and a 4th one over there, the yellow blobs, that is producing these images of a background galaxy. So in this case here, the yellow blobs are the fish tank, and the blue arc is the fish. And there's multiple images of the fish. And notice what's happening here. There happens to be a little ball of mass just in front of one of the images. And so you see this image here is split in 2. So it's kind of like, I don't know, maybe you've seen this. You're driving and a rock falls on your windshield, and there's a little dent in your windshield. If you try to look through the dent, you'll see that the images get to you perturbed. This is the same thing. This little perturbation here in the gravity is changing how the background objects will appear. So this is what I'm looking at. Of course, on much smaller scales, I want to detect these little dinks in the fabric of the universe by looking at how background objects get blurred and get smeared. So this is difficult. It takes a little bit of time, and it takes a lot of precision in the images. But at the moment, all the data we've taken so far are consistent with the simplest kind of cold dark matter, what we call vanilla cold dark matter, which is, for particle physicists, would be a WIMP. WIMP is a weak interactly massive particle. It's not like a particularly wimpy person or anything like that. It's the name they use for this stuff. There are WIMP machos. There are all sorts of funny names. Physicists have a strange sense of humor, but let's not go there. Yeah. But the thing is that so far, we've really only been able to scratch the surface of this, literally. We've only been able to tell you it's consistent with the kind of more basic flavor of dark matter. But in order to make progress, we need to get sharper and sharper images. We need to get to the point where we can detect these little bumps on finer and finer scale. Let me conclude with some thoughts about how we're going to do that. First, I want to remind you what the questions are. What we want to learn is what is dark matter, and you see is here is the most important thing. So what is the essence of it? What is it made of? And the way in which we learn what something is sometimes is we first learn what it is not. Okay? We have a list of possibilities and we rule them out one by one. We want to do the same thing for dark energy. Okay? We want to know what it is, and so we're trying to rule out things that dark matter is not. And at the end, if we can answer these 2 questions, I can finally retire. Well, maybe even just one of the 2. But we as humans, we will have learned what 95% of the universe is made of. And I bet you that some of you tonight will go home and will lose your sleep over this. I personally do. Some nights, it's like, what the heck? How can we not know what 95% of the universe is made of? So I hope this question stays with you for a little while. And so how do we get there? One very important technology is adaptive optics. You've seen these beautiful pictures of Keck or other telescopes shooting lasers at the sky. What we're doing there is trying to use artificial stars to correct for the blurring of the atmosphere in order to get the sharpest possible images of the sky. Because what I really want is very, very sharp images, because I need to detect these little dents. I need to detect these little dents in my windshield, okay? And the smaller these dents are, the more sensitive I am to different kinds of flavor of dark matter, dark energy. And Keck already has arguably the best adaptive optics system in the world for this kind of work. But this is not enough yet. We need to make further improvements in order to solve this mystery of the remaining 95%. And we can do this. There are ideas on how to do this. The technology is being developed. So I think this is something really exciting that we can all look forward to. And I want to conclude with something. Sometimes, my students ask me, so why should I do astronomy? Why do we do astronomy? What is the point of doing astronomy? And I thought about this for a long time, and the best answer I can come up with is the following, that animals tend to be happy with, food and shelter and the primary needs of life. But humans tend to wonder and want other things. Humans tend to do things like art or knowledge, or are curious about things that have no practical implications about their lives. And these things are not really relevant for our day life, but they're the one things that when we pursue them, eventually lead us to see the world in different ways and maybe to develop things that have huge implications for our lives. I would argue that we as humans, we would not be who we are if we didn't do useless things. It's the fact that we do useless things that make us human. And I'm sure you've had your fair share of time spent on useless things in your life. But those are probably some of the things you have enjoyed the most. Okay? So I want to conclude with this quote from Hannah Arendt. It's not quite at the level of Yogi Berra, but I think it's... So she says, 3 great events stand at the threshold of the modern age and determine its character. The first one is the discovery of America, the change our view of the world. The second is the Reformation, changed the view of God for Christians. And third, the invention of the telescope and the development of a new science that considers the nature of the Earth from the viewpoint of the universe. So this is what the telescope does for us. The telescope allows us to go outside of the Earth, outside of ourselves, and look at us from the point of view of the universe. And I just told you that when we look at ourselves from the point of view of the universe, we discovered that we are just the 5%. And 95% of the universe is something we would have never seen if we did not have telescopes. And adaptive optics is the equivalent of the Copernican revolution, of the Galilean revolution for our times. So I would like to end here and tell you that this sums it up. The mass of the universe is really what I'm after.